Today we're going to be talking about section 3.3, which is on variation. Now there's lots of different variation problems. We're going to start with the most basic of which is called direct variation. Now direct variation is written like this: y is equal to k times x, where k is not 0, because if k was 0, then we'd have y equals 0 all the time. So this is direct variation. It basically says that when you have some input x and you multiply it by some constant of variation k, in fact, that's our next vocab word, constant of variation, it's k. When we multiply it by some value of k, we end up getting a y out of it, right? And so some easy ways to think of this would be like y equals 3 times x, right? Because 3 times, let's say 1 is 3. And so you put in an x, you get out a y. We also know that this is also a linear equation, and it's a problem when basically our slope is 3. Now, the difference between direct variation and linear equations is that direct variation will always pass through the point 0, 0, because we're not going to add or subtract anything to it, right? And so you can think of it that way, that direct variation is a linear equation that just for sure is going to pass through the point 0, 0. Now, we don't always use x's and y's. We might use other variables as well. But let's take a shot at a problem. Okay, so we want to look at a problem that has direct variation, right? And so let's say that we have two values, d and g, okay? And this is what we know about d of g. If d equals 16, then g equals 14, okay? So what is the value of g when d equals 25? Okay, so basically it says this, that I have two values, d and g. Now this time I'm not using x's and y's, but that's okay. There's still a constant of variation. I'm still multiplying g by something to figure out what d is, right? So I'm going to set it up like this, okay? In fact, might even make it easier if we say we're multiplying d by something to get g. All right, so let's do this, okay? Both would get you the right answer, but essentially it goes like this, okay? G is equal to some constant k times d. Okay, so let's plug in our values. So in the first one, 14 is equal to k times d. All right? But if we think of it the other way, it says g is equal to k times d. In our case, it'd be g is equal to k times 25. Now, thinking of it this way, if we can solve it so that they're both equal to k, then they be equal to each other. So we're actually going to set it up so that that happens, right? We're going to divide this by 16, divide this by 16. And if I divide this by 25, divide this by 25, I find that I get k equals, right here, k is equal to 14 over 16, and over here, k is equal to g over 25. So they're equal to each other. So we can say 14 over 16 is equal to g over 25, right? And so how do we solve a proportion problem like this? Well, we basically just multiply, right? So I'm going to multiply 25 by 14, okay? And so I'm going to get 25 times 14 over 16. And I can do this on my calculator, okay? And when I do that, I get 21. So over here, G is going to be equal to 21.875. Now, we're going to look at the next section, which is called modeling with direct variation. So we can actually model real-world applications, right? It says this: a kite company produces kites whose length vary directly with their width. Okay, so excuse me. Length is equal to some constant k times width. Okay, so think about it. It might be the fact that, it's twice the width or something like that. So here's a problem. If a kite whose length is 80 centimeters, okay, all right, so think about it. Length is equal to 80 centimeters. okay, and has a width of 65 centimeters, what would be the width, okay, don't know, of a 96 centimeter long kite? Okay, so we look here. Okay, we have three values. We're missing one of them. And so we can set it up. We actually have it set up right there. L is equal to K times W. So let's just, okay, let's try it. So let's see. I'd say 80 is equal to K times 65. And I have 96 is equal to K times W. Don't know what it is, right? And so my job then is I need to solve this. Okay, I can solve them both for Y, or for K, excuse me, because if they're both solved for K, they're both solved for the same thing. So divide by 65, divide by 65, okay, divide by W, and divide by W. Now they're both equal to K, right? And so we're going to set up like this. We're going to say 80 over 65 is equal to 96 over W. Now, a problem like this is a little bit more challenging, right? And so before it was just we multiplied by 25 and then you could divide by 16. This one's a little bit more challenging, but that's okay. We can still do it. All right. So what we're going to do is we're going to say 65 times 96 is equal to 80 times W. So 80W is equal to, move myself out of the way here for a second. All right. 96 times 65. Okay. And that's going to be 6,240. Now we divide by 80, and we find W to be 78 centimeters. Okay, so for this one, it makes sense. If it got longer, the width would also have to increase as well. Okay, because this is direct variation. It happens. Now, the next thing we're going to look at is something a little bit different. It's called inverse variation. And inverse variation is kind of like what it sounds like. So in inverse variation, we actually have this equation right here. Y is equal to now K divided by X. Instead of multiplying direct variation, it's the inverse. We're actually taking our constant of variation and dividing it by X. Now, another way that this is written, and this is more often how it's written, is this. K is equal to Y times X, which basically is what sets up our direct variation. As Y increases, X is going to have to decrease to create that constant K, right? So if Y doubles, X is going to be half of it. Or if Y triples, or if X triples, Y is going to have to be a third of it, right? And so that constant change, that direct variation is always going to change too. Okay, so let's look at a problem that has inverse variation. Okay, okay, so it says suppose that X is, okay, I'll just give you some numbers. Suppose X is equal to 8.4 and Y is equal to 1. And X varies inversely with Y. Find X when Y equals 4. Okay? Find X when Y equals 4. Okay, so let's set it up like we did before. Again, we don't have a K, and that's all right. That's no big deal. But we can do this, okay? We're going to say that 1 is equal to K over 8.4. Or it may be easier to use this one, right? And so we're actually going to say K is equal to 1 times 8.4, right? We also know over here that K is going to be equal to 4 times X, which is just 4X, right? And so since they're both equal to K, they're equal to each other. And so we're going to say 8.4 is equal to 4X. Now, how would we solve a problem like this? Well, we're going to divide by 4. Divide by 4. And we find out that X is equal to 2.1. Okay, which makes sense when you think about it, because since Y is going from 1 to 4, it's increasing times 4. So its X is going to have to be a quarter of it, or 1/4 of it, right? Okay. Now, let's say we model something with inverse variation, and this happens actually a lot more than we think. A good example of this would be like supply and demand. As supply increases, Okay, we're going to want demand to increase as well. But as supply decreases, okay, um, well, I guess that's more direct variation, but you know what I'm saying. All right. So, okay, so here is one right here. It says if it takes 13 days for 12 people to harvest a field, how many days would it take for 4 people to harvest a field? So think about it. Less people, probably going to take more days, right? So that's a good inverse problem. Okay, so let's go back. So days is going to equal 13, and people is going to equal 12, right? So 12 people take 13 days. Now we want to figure out how many days when the people is only 4. Okay, so if we think of it like this again, k is equal to, let's say, days times people, right? And over here, k is equal to days times people. And so we say k is equal to 13 times 12. And over here, k is equal to 4 times d, right? And so since they're both equal to k, they're both equal to each other. And so 13 times 12, if you didn't know that off the top of your head, like I didn't, is 156 equals 4d. Divide by 4, divide by 4, and d is going to be 39. So significantly longer for 4 people to harvest wheat fields. Okay? All right, next we're going to talk about joint variation. Now, joint variation is something a little bit different, okay? It's not something that we regularly do, okay? So here's our equation right here, okay? It's y is equal to k times x times z. So now what's happening is it's like direct variation, but there's a third number, right? Or a third input or a third value, right? And so we would say that y, I'll write this down because this is important. Y varies jointly as x and z. Okay, so basically it's saying that y is going to change when both x and z changes, right? And so that k, that constant k, is going to stay the same. But our x's and z's are going to be kind of a little bit different, okay? So let's write a problem, okay? So I have one that says, suppose that A, we're talking about area, is equal to 24 square inches, okay? And it says B is equal to 6 inches, right? And H is 8 inches. And so find what H is, okay? So here, we don't know what H is. When the base of um, when our base is 10 inches and our total area is 100 square inches. Okay. So we have a problem here, okay, where we're looking for we have one that says the area is going to be 24 square inches when the base is 6 and the height is 8. Now, if we think of it this way, okay, we're going to say A is equal to some constant K, we don't know what that is, times B times H, okay? And so in our problem, right, we would write it in our first one, we'd say 24 is equal to some K times 6 times 8. Now, you're probably already figuring it out in your head that 6 times 8 is 48. So we're going to say 24 is equal to 48K. So what's K going to be? Well, K is going to be 1/2, right? And so we figure that out we say k is equal to 1/2. If you're not sure how we got 1/2, you just take 24 divided by 48. It's 1/2. Okay, so now that we know what k is, now we can use that to solve our missing h right there. So we're going to say 100 is equal to 1/2 times 10 times h. Okay, and so then when we simplify a little bit, we get 100 is equal to 5 times h. We divide by 5. We divide by 5. We find that h is equal to 20 inches. Okay, so that's where there's multiple values in there that we can actually use to solve. Okay, very good. All right, now we're going to talk about the last type of variation that we're going to cover, which is combined variation. Combined variation's a little bit different. It's kind of like joint variation, kind of like inverse variation. In fact, it's pretty much a combination of both, right? And that's why we call it combined variation. Okay, so combined variation is this: y is equal to k times x over z. Okay, over z. Now, how would we read it? Okay, this is important. So I'm going to write this down. Okay, it says this: y varies directly as x and inversely as z. Okay, so it's saying both directly and inversely. So if you see both, okay, so if you just say directly, it's direct variation. If you just see inverse, it's inverse variation. But if you see both in it, direct and inverse, that's combined variation. And that's our key phrase that we need to look for, okay? All right, so let's look at a problem, okay? All right. So here's a problem. It says to move a car 200 feet in 75 seconds, the car's engine must deliver 152 kilowatts of power. Find the distance when the car moves at 189 kilowatts of power delivered for 90 seconds. Okay, so there's going to be some important information that we're going to need to know from that. Okay, so we have to remember that the car's engine varies directly with the distance and inversely with the time. Okay, so we'll think about it like this. Okay, so so our power P is equal to some constant of variation K directly with the distance D, but inversely with time. Okay, so power is equal to some value times distance divided by time. Okay, and so let's look at a problem. Okay, I guess I kind of did that backwards for you. But in this problem right here, it says we want to move our car 200 feet. Okay, so obviously that's distance, or excuse me, 2,000 feet is going to be our distance. Okay, and we want it in 75 seconds. So 75 is going to be our time. Okay, so to do that, our power must be 152 kilowatts of power. Okay, so there we go. We have P, we have our distance D, and our time T. Okay, for one example. Now it says find the distance. Okay, so distance is unknown. I'll do this in a different color. Distance is unknown when we want our time to be 90 seconds, right? And we want our power to be 189 kilowatts. Okay, so now again, we just have it set up. Why don't we take the first one, what's in green, and let's solve it for K. And if we can solve for K, then we can plug it into the second one. Okay, so again, you're seeing that there's lots of different ways we can solve these problems, right? We don't have to solve them all the exact same. Now, just because I solved one of these problems one way doesn't mean you have to do it that way. So let's take a shot at this. All right, so the first one, we want 152 kilowatts of power is equal to K times 2,000 divided by 75. Now, how would you solve this problem for K? Now, there's lots of different ways you can do it. In my opinion, the easiest is to multiply by 75. Multiply by 75. And so when we do that, 75 times 152 is going to be 11,400, which is equal to 2,000 K. Divide by 2,000. Divide by 2,000. Okay, and so when we do that, okay, we get K is equal to 5.7. So our constant of variation for this K is 5.7. So now let's use that information and plug in the values that we know to find out what D is. Okay, so, all right. So in our problem, we want our power to be 189. Okay, that's what we want it to be. Our K now is 5.7. Our distance is unknown, but we're dividing by our time of 90 seconds. Okay, so now it's our job to solve this out. Times 90 times 90. Okay, I'll keep moving along with it. And so 90 times 189 is equal to 17,010, which is equal to 5.7 times our distance D. Divide by 5.7, divide by 5.7. And we find that our distance, I'm going to round it to the nearest tenth here, is 2,984.2, what is that, feet. Okay? So there we are. So like I said before, there's lots of ways to solve these types of problems. The easiest is just to plug in the values that you know. If you're nervous about setting up a problem, it's no big deal. Try your best. Most of the time when they just give you an X and a Y or a G and a D like we did in that one, you can set it up either way. It doesn't matter. G varies directly with K or D or whatever. It doesn't really matter. Okay, you don't have to worry about that. So put your mind at ease a little bit. But for the rest, read the wording, figure out what it is. If you have trouble, let me know.